Good afternoon, everyone. A warm welcome to all of you to the fifth session of the webinar series on Cellular Automata. Thank you for joining us in this series, which started in August 2020. So, on behalf of the organizers, I will take this opportunity to just invite you for the next installment of the series also, that is scheduled on 17th of December 2020, where Professor R. Ramanujam, fondly known as JAM, from Institute of Mathematical Science, Chennai, will deliver his lecture. So today we are so lucky to have among us Professor Kenichi Morita, who will deliver his talk on simulating Turing machines in a simple reversible cellular automata. So Professor Morita needs no introduction. Still, for the sake of completeness of the event, please allow me to give a brief introduction about him. Professor Morita received a PhD in engineering from Osaka University in 1978, and he was a professor of the Graduate School of Engineering, Hiroshima University, where he is still working as a professor emeritus. He is a pioneer in the research of automata theory, cellular automata, reversible computing, and formal language theory. Professor Morita is renowned for his works on two-dimensional language accepting automata, complexity of Turing machines, universality of cellular automata, regular and context-free array grammars, and undecidability. He has introduced the concept of partition CA in the domain of CA. He has written more than 100 articles, most of which are similar in nature. Some of his high-impact works include findings on parallel generation and parsing of array languages by means of reversible automata, construction of a data from Fredkin gates, solving a squared synchronization problem in reversible CA, self-reproduction in reversible CA, reversible two-counter machines, solutions of NP problems in hyperbolic cellular automata, which are very interesting. I found it so much interesting. Reversible P system, a new universal reversible logic element with memory and reversibility in asynchronous CA. As a tribute to Professor Morita's ideas and achievements in theoretical computer science, reversibility, and computationally universal mathematical machines, some of his colleagues, collaborators, students, and friends who presented some essays, and which is a classic book on reversibility and universality. That is a must read for us actually. So we are eagerly waiting to listen to you, sir. Over to you.
Thank you. Thank you very much for your introduction. Now, at first, I would express my great thanks to the organizers of this webinar, especially Kamarika, for your invitation. It is a great pleasure for me to give a talk in this occasion. Okay, I now use my slides. Okay. Can you see my slides?
Yes.
Okay, today's talk is on a problem of simulating Turing machines in a very simple reversible cellular automaton. An outline of my talk is as follows. We argue how computing is performed in a reversible cellular automaton having the following extremely simple local function given here. I will explain reversible Turing machines can be realized in this cellular space in the cellular space shown in this picture below. Okay? How the configuration evolves will be shown using a cellular automaton simulator GODI. later. Okay. These are the contents of the talk. First, reversible computing and reversible cellular automata are explained. Second, an elementary triangular partitioned cellular automaton, ETPCA, in short, is defined. In the following, this framework, ETPCA, will be used. Third, I focus on the specific ETPCA number 0347 and investigates its interesting properties. Finally, reversible Turing machines are composed in the cellular space of ETPCA 0347. Now, at first, I explain briefly reversible computing and reversible cellular automata. Reversible computing is a paradigm of computation that reflects physical reversibility, a fundamental microscopic law of nature. A reversible cellular automaton is a spatio-temporal model having reversible dynamics. An RCA, reversible cellular automaton, is regarded as one of the reversible computing models. Based on my studies on these topics, I recently published a book, Theory of Reversible Computing. It also contains reversible cellular automata. Very roughly speaking, reversible computing is a backward deterministic system. As in this figure, every computational configuration has at most one predecessor. Therefore, no such configuration exists. Though its definition is rather simple, it reflects physical reversibility very well. There are several reasons of studying reversible computing, because reversibility is one of the fundamental microscopic physical laws of nature. Second, therefore, it is important to investigate how computation can be carried out in a reversible system. This is because the size of future computing system will surely become nanoscale ones. It also relates to energy consumption in computing and to quantum computing. We shall see that despite the reversibility constraint, they have a very high capability of computing. Therefore, reversible computing also gives a new insight for unconventional or future computing systems. There are several levels and models of reversible computing. In the lowest level, reversible physical system exists. Then the levels of logic element, logic circuit, finite state machine, and universal computing systems follow. It is known that any reversible model in the higher level can be realized in the lower level. A reversible cellular automaton itself is in the highest level. But these levels also appear inside the reversible cellular automaton when realizing universal computing systems in it. This figure shows such a situation in reversible cellular automaton. In reversible cellular automata, microscopic law of evolution exists in the lowest level. In the next level, if we find useful phenomena in the cellular space, they are identified as primitive functional modules. Using such useful phenomena, a logic element module is composed. Then logic circuits are composed out of logic elements. Finally, universal computing systems are constructed combining logic circuit modules. Later, afterwards, I will explain in more detail. A cellular automaton is a discrete model of spatial-temporal phenomena. Although you may know cellular automata very well, here I describe a definition of a cellular automaton on the square tiling. It is defined by a quintuple Z square Q N F small f and sharp. Okay. Z square is a set of all points with integer coordinates. Q is a non-empty set of a finite set of states. N is an element of Z square to the mth, called a neighborhood. It is usually represented by n tuples of n tuple of points, n1 to nm. Okay. Small f is a local transition function, or local function in short. This is a function from Q to the mth to Q. Sharp is a quiescent state such that that satisfies this equation. We also allow a cellular automaton having no quiescent state. A configuration and the global transition function are defined as follows. Let A be a cellular automaton. A configuration of A is a function that assigns a state in Q to each point in Z square. Let conf A denote all configurations over Q. Applying the local function small f to all the cells in a configuration simultaneously, we obtain a global transition function, or global function in short, large F. More precisely, it is defined by this figure, but global function is defined as usual. Okay. On the other hand, reversible cellular automaton, RCA, is defined as follows. here, a reversible CA, RCA is a CA whose global function, large F, is injective. It is regarded as a kind of spatio-temporal model of a physically reversible space. RCAs, reversible cellular automata, have high capability of computing, such as computational universality, and so on. However, designing two-dimensional RCAs is not so easy if we use the framework of standard CAs. Generally, it is not decidable. Given a cellular automaton, it is not decidable to know it is reversible or not. Okay, it was shown by Yarko Kari. But there are a few methods for designing reversible cellular automata. Using the Margolis neighborhood, using second-order cellular automata, and using partitioned cellular automata. But here, I use the last method, partitioned cellular automata, PCAs. A partitioned cellular automaton, PCA, is a subclass of usual cellular automata. It was introduced to make it easy to design reversible cellular automata. Each cell is further divided into several parts, and each part has its own state set. For example, this is a two-dimensional four-neighbor PCA, okay, with square cells. In this case, each square cell is divided into four parts, like this. And the next state of a cell is determined only by the adjacent parts of its neighboring cells, like described in this figure. Okay? In the following, we use the framework of a triangular partitioned cellular automaton, TPCA. Since it has only three neighbors, its local function can be simpler than a square PCA. An elementary TPCA, ETPCA in short, is an 8-state rotation symmetric TPCA, the simplest subclass. In this talk, we focus on the particular reversible ETPCA, number 0347. I will define later. Okay. In a triangular partitioned cellular automaton, a cell is divided into three parts, like these, okay? Each of which has its own state set. Next state of a cell is determined depending on the adjacent three parts of its three neighbor cells, as shown in this figure. This is a formal definition of a TPCA. But intuitively, it is just I have it is I have just explained. Okay, a triangular partitioned cellular automaton TPCA P is formally defined as follows. Here, Z square is the same as before. L, D, and R are non-empty finite sets of left part, downward part, and right part states. And NU and ND are neighborhoods for up triangle cells and down triangle cells. Okay. And small f is a local function. Note that since TPCA is defined on Z square here, up triangle and down triangle cells have different neighborhoods, NU and ND. It is, of course, clear from this figure. Up triangle, for example, this is an up triangle. It has three neighbors, left neighbor, downward neighbor, and right neighbor. Okay, but down triangle have left neighbor, upward neighbor, and right neighbor. Therefore, neighborhood is slightly different for upward, up triangle and down triangle. A configuration is defined in a similar manner as in the case of a usual CA on a square grid. On the other hand, the definition of the global function is slightly complicated since it needs projection functions, projection PRL, PRD, and PRR. For example, PRL chooses the state L from a combination LDR. PRD and PRR are similar. Okay? But the meaning of this formal definition is clear from the previous figure. Therefore, I omit a detailed explanation for this formula. Namely, it is clear from this figure. Next state of this triangular cell is determined only by these three parts. Okay. It has been shown that in a PCA, partitioned cellular automaton, local injectivity and global injectivity are equivalent. It is relatively easily proved for any partitioned cellular automaton, one-dimensional or two-dimensional, or square cellular automaton, or triangular one, and so on. From theorem 1, we can obtain next corollary. A PCA P is reversible if and only if its local function is injective. Therefore, by this corollary, we can obtain a reversible PCA by designing its local function is injective. Therefore, such a framework of a PCA helps us to design reversible cellular automata. Next, I define elementary TPCA, ETPCA in short. It is a simple subclass of TPCA, triangular partitioned cellular automata. ETPCA is defined as a TPCA that satisfies the following two conditions. The first one is each part has only two states, 0 and 1. Therefore, each cell has 8 states in total. Okay. And second, its local function is rotation symmetric. It means that if there exists a rule like this, then rotated ones by a multiple of 60 degrees also exist. This is an example of an ETPCA. Number 0347. In ETPCA, the local function of it can be described by only 4 local transition rules because it satisfies rotation symmetry. An ETPCA is specified by a 4-digit number W, X, Y, Z, where W and Z are either 0 or 7, and X and Y is in the set 0, 1 to 7. Note that W and Z must be 0 or 7 because of rotation symmetry. W or Z, W and Z must be either 0 or 7. But X and Y can be any one of these 8 possibilities. And we can choose any combination among these possibilities. Therefore, there are 256 ETPCAs in total. Reversible ETPCAs are as follows. We can see the proposition 1 very easily. Let P be an ETPCA. If any pair of distinct local rules of P have different right-hand sides, then its local function is injective. Actually, local function of ETPCA 0347 is injective, since no distinct rules have no pair of distinct rules have the same right-hand size. Okay. For example, ETPCA 0337 is not injective, therefore not reversible. But 0347 is injective and thus reversible. By this observation, we have a proposition 2. ETPCA WXYZ is reversible if and only if WZ is either 07 or 70, and XY, pair of XY is this from this set or from this set. Then all the right-hand sides are different. Hence, such ETPCAs are reversible. And therefore, we can see there are 36 reversible ETPCAs in total. Next, we focus on ETPCA 0347. We fix the number, ID number 0347. It is a reversible ETPCA. It is the most interesting in the class of ETPCAs, as you see in the following. Actually, it shows very complex behavior. Now, we start with a single particle pattern. There is a single particle. Okay, can you see? And watch how it evolves in ETPCA 0347 by a simulation movie. But please note that an animation movie may not be seen smoothly if the network speed is not sufficiently high. Okay, anyway, I started. Can you see? It generates a disordered pattern and a moving object called a glider. Here is at the right side, a moving pattern is generated. But on the left side, some disordered pattern, random-like pattern is generated. I myself started with this pattern and thought it will surely be interesting cellular automata, since such glider, space-moving pattern exists. By the way, I use a CA simulator, Gori. Gori is a free software for simulating cellular automata developed by Trevor, Rockiki, Hutton, and others. I use Gori for simulating very large configurations of reversible ETPCA 0347 in high speed. Well, I myself created this simulator like this for small configurations, but it cannot be used to simulate very huge configurations. Therefore, for such configuration, I use Gori. Now, I'll show Gori, and on this simulator, I created a rule file for ETPCA 0347. First, look at this configuration. It looks like a random configuration. Of course, Gori is for square cellular automaton. It is a simulator for square cellular automaton. Therefore, triangular cellular automaton should be simulated on square cells. Here, green dots are downward triangle, and yellow dots are upward triangle. Therefore, two kinds of cells exist. Okay, in such a way, triangular cellular automaton is simulated. But anyway, how do you think this configuration evolves? Okay, it shrinks and shrinks. It is an implosion, and then explosion occurs. Okay. At the edge of this configuration, many gliders are generated. Okay, can you see? Okay. We go back to ETPCA 0347. There are three useful objects in ETPCA 0347. They are glider, block, and fin. Glider is a space-moving object that swims in the cellular space like a fish or an eel, like this. Okay, it will be used as a signal when we construct Turing machines. The second one is a block. It is a pattern either of the following two. Block is stable in the sense it does not change its pattern if no other object touches it. The third object is a fin. It is a pattern that rotates with period 6, like this. And it can travel around a block or sequence of blocks clockwise, like this. These three objects are really useful, as we shall see next. Okay. Now we observe how objects in ETPCAs interact. By colliding a glider with blocks or other gliders, we can observe interesting phenomena. In particular, move direction of a glider can be controlled by them. Patterns that show useful multiple phenomena are used as functional modules. Colliding with a glider with a single block like this, it is first decomposed into a body and a fin. Decomposed into body, left, and a fin. And the fin travels around the block twice. Then a glider is reconstructed like this, okay? And it goes backward. I will show once more. It is decomposed into body and fin. And these are combined, and again, a glider is formed, reconstructed. By this, we can realize a backward turn module. Next, a sequence of 3 blocks works as a 120-degree right turn module, like this. First, they are split into 2 parts, but again, a glider is reconstructed. I will show once more, okay? This is a 3-block case, but sequences of 2 blocks and 5 blocks also work as right turn modules. Left turn module is a little bit complicated, but anyway, first it is decomposed into 2 parts and reconstructed, and left turn is realized. This is a U-turn module. Okay. Anyway, by these modules, trajectory and timing of a glider, namely signal, is adjusted. I will show using Gori. In this configuration, there are 2 gliders here and here, okay? And there are many turn modules, right turn modules, U-turn modules, backward turn, and left turn, okay? Look at lower glider. First, this is a left turn module. Right turn module. Again, this is also a right turn module. U-turn module. And again, right turn module. This is a backward turn module. And so on. Okay. On the other hand, colliding a glider with other glider, some interesting phenomena appear. From 2 gliders, we can construct 3 gliders. Like this. Symmetrically, from 3 gliders, 1 glider is annihilated. This is a symmetric situation. Okay. Therefore, 1 glider is reversibly deleted. Using such phenomena, we can construct a glider gun and glider absorber. This pattern on the left side is a glider gun, and this is on the right side, a glider absorber. The left side, from 2 gliders, 3 gliders are generated. From 2 to 3 are generated. Okay. On the right side, this glider is deleted, reversibly deleted. Therefore, it acts as a glider absorber. Okay. By appropriately interacting gliders, we can construct a Fredkin gate, which is a reversible logic gate in ETPCA 0347. A Fredkin gate is a 3 input, 3 output reversible logic gate. The first input, C is a control input. And if C is 0, then remaining 2 inputs are connected to 2 outputs in a closed manner. But if C is 1, then they are connected in parallel. Okay. Some kind of switching gate. And it is known by Fredkin and Toffoli. Fredkin gate is universal for constructing reversible machines, reversible Turing machines or like that. And Fredkin gate can be composed of switch gate and its inverse. Switch gate is 2 input and 3 output logic gate. And this can be implemented in ETPCA 0347 like this. Okay. 2 signals, C, control signal, and other signal, X, comes from here and here. Of course, only one signal of, for example, C exists, then it goes straight ahead. X goes straight ahead. Okay, but both C and X exist, then X is reflected in this way. Therefore, some switching function is realized. Like this, okay? And by combining two switch gates and two inverse switch gates, we can compose a Friedkin gate, like as shown in this figure. And the configuration in ETPCA 0347 is like this. I will also show this configuration using Gori. It is a bit complicated. Here is a switch gate module. There are many term modules, right term modules, but they are only used to control the direction of an input signal and its timing. By using two switch gates and two inverse switch gates, a Friedkin gate is simulated. There are 8 cases of input pattern, and they are given sequentially, like this. Anyway, this signal goes through these modules, and as a whole, in gate is realized. Can you see? It is a little bit difficult to see because very complex figure. Okay. Now, since a Friedkin gate is realizable in ETPCA 0347, it is in principle possible to construct reversible Turing machines in it. Therefore, ETPCA 0347 is computationally universal. However, as a practical construction method, using logic gates is not good, because Friedkin gate itself is very complex like this. And also, adjustment of timing of 2 or more signals is necessary. Modules for Turing machines become very huge. Therefore, logic gates are not useful in cellular automata. So here we do not take this approach. Using reversible logic gates approach is not used. Instead, we use reversible logic element with memory, 1-bit memory. In this case, there is no such timing problem, since a signal can be given at any time to each element. Therefore, we take the latter method. Now, the last section is devoted to composing reversible Turing machines in ETPCA 0347. Here, modularization method for composing reversible Turing machines, RTMs, is taken. And reversible logic element with memory, RLEM, rather than a logic gate such as Friedkin gate, is used. RLEM is used. And any RTM, reversible Turing machine, can be constructed in a systematic manner very concisely. In this manner, modularization method. Okay. In the lowest level, a simple local transition function of ETPCA exists. In the next level, signal control modules are formed by utilizing various phenomena observed in the cellular space. Then, combining signal control modules, an RLEM, reversible logic element with memory, is created. Some useful circuit modules are then designed and composed out of RLEM modules. And finally, reversible Turing machines are constructed, combining circuit modules. Here we give a definition of a Turing machine as a standard model of computing. Here, a Turing machine is defined by a 6-tuple, but I skip this formal definition. Instead, I use some examples. But anyway, Turing machine's movement is described by a set of quintuples like this. Okay. Depending on the present state of the finite control and the red symbol, a Turing machine determines the following: symbol to be written, shift direction of the head, and the next state. I again say, from the present state and the red symbol, next written symbol and shift direction and the next state are determined. This is described in such a quintuple form. A reversible Turing machine and its universality is defined as reversible Turing machine is defined as follows. Turing machine T is called reversible if the following conditions hold for any pair of distinct quintuples, this one and this one. Namely, if the next states Q1 and Q2, next state Q1 and Q2 are the same, then the written symbols S1 prime and S2 prime are different, and the shift directions must be the same. Such a Turing machine is called reversible. Okay. As for reversible Turing machine, the following theorem have been shown by Bennett. For any irreversible Turing machine, we can construct a garbageless reversible Turing machine that simulates the former. I now give a very simple example of reversible Turing machine, T Parity. It is defined by only 5 quintuples. Okay. For example, first quintuple is if the Turing machine reads the symbol 0 in Q0, then it writes symbol 1 and shift the head to the right and becomes the state Q1, and so on. It accepts a given unary number n is even. It is a little bit confusing. But anyway, parity is checked. And this is a reversible Turing machine because, for example, if the next state Q1 is the same, then return symbol are different. This is 1 and 0. And shift directions are the same. Therefore, this Turing machine satisfies the reversibility condition. For example, if a unary number 2 is given to this Turing machine, then it is accepted. And here all the red symbols are complemented. I will construct this Turing machine in the cellular space of ETPC 0347 later. The second example is a little bit complex. It is T power. It is defined in this way. We assume a string 1 to the nth, namely n copies of 1 is given. Then it accepts if n is a power of 2. Okay. For example, if we give a unary number 8, then it is accepted. For example, it works in this way. It finally holds and accepts for since a given unary number is 8. Okay, and we can check this is indeed a reversible Turing machine. Now we next construct reversible Turing machine using reversible logic element with memory. It is a kind of reversible sequential machine having internal states. Namely, from the present state P and the input AI, it determines the next state Q and the output Sj. Okay? In this case, input signal represented by a particle interacts with a state P. Therefore, there is no need of synchronizing many signals. Therefore, construction of Turing machine is very much simplified. A sequential machine of mealy type is defined in the following way. But it is just as I have explained by using this figure. Therefore, I omit this formal definition. But anyway, sequential machine M is called a reversible sequential machine, RSM, if the transition function delta is injective. And the reversible logic element with memory, RLEM, is an reversible sequential machine such that the number of input symbols is equal to the number of output symbols. Such a reversible sequential machine is called a reversible logic element with memory. Okay? Anyway, if sequential machine is reversible from the situation at the time t plus 1, we can uniquely retrieve, we can uniquely determine the configuration of sequential machine at the time t. From the next state q and the output sj, we can uniquely determine the previous state p and the input. Okay? Such a machine is called reversible sequential machine. A particularly important reversible logic element with memory is a two-state element. For example, RLEM 431. 4 means it has 4 input lines and 4 output lines. And 31 is a serial number in the class of two-state, 4-symbol machine. And 431 have the following transition function. For example, if it is in the state 0 and input is A, then next state is also 0 and output is W, and so on. Such a transition function is depicted in a graphical form in this way. Okay, solid and dotted lines indicate input and output relation. Okay, and solid line means that the state changes to another. Dotted line means the state remains unchanged. Therefore, if a particle, input particle, goes through a dotted line, then the state is kept unchanged. Okay, but if a particle, input particle, goes through a solid line, then state changes to the other. Okay. Sorry. It has been shown that almost all reversible logic element with memory, two-state RLEMs are universal. RLEM is called universal if any RSM is simulated by a circuit composed of it. And almost all two-state RMs are universal. Only 4 are non-universal or unknown. Okay. Anyway, 431, RLEM 431 is universal. Therefore, it can construct any reversible sequential machine. And reversible Turing machine can be composed of reversible sequential machine modules, as we shall see later. Okay. This is an example of a circuit composed of RLM 431. If a particle goes through a dotted line, then the state does not change. But a solid line, then state changes like this. Okay. By using such a circuit composed of RLM 431, we can construct any reversible Turing machine. This is an example of implementation of T Parity. I have just shown, this is an example of I have just shown. On the left-hand side, there is a finite state control of this machine, T Parity. On the right-hand side, there is a tape unit, but of course, it consists of infinite copies of tape cells. Okay. On each column of this 9 elements represents a tape square, and at the top element symbol, tape symbol is stored. In this case, 0, 1, 0 are stored in the tape squares, in these tape squares. Okay. It is very complicated, and therefore today I cannot explain the details. But anyway, T Parity, parity checking Turing machine is simulated by this circuit. Input is 0, 1, 1, 0. Therefore, input should be accepted. By giving only one particle from begin port, it starts to simulate. Okay. But it takes very much time. Therefore, middle part is fast forwarded. Anyway, finally, a signal appears from accept port. Okay. In such a way, any reversible Turing machine can be implemented by RM 431. Okay. Now, I consider how we can realize RLMs in ETPCA 0347. Such a simple cellular automaton can simulate reversible logic element with memory. Here, 2 states of RLM 431 are kept by a fin. This is a fin, okay? And state change is possible by shifting it by a glider. By colliding a glider appropriately, position of a fin is shifted. This is a case of pulling. Okay, this is a case of pushing. In this way, position of a fin can be changed. By using such phenomena, state change of RM 431 can be simulated in ETPCA 0347. This is a complete configuration in ETPCA 0347 that simulates RM 431. Okay. Around the center of this pattern, there are two small red circles. They show possible position of a fin. Okay, if a fin is at the lower circle, then we assume it is in the state 0. But it is in the upper part, upper circle, it is assumed to be the state 1. Okay, and by giving a glider signal from either A or B or C or D input ports, the operation of RM 431 is properly simulated. This is a configuration of RM 431 in the cellular space of ETPCA 0347. Around the center of this pattern, there is a fin, okay, rotating like this. Okay. Now it is in the lower position. Therefore, it is assumed that this element is stay in the state 0. And glider signal is given from this input port, in this case, the input port. Okay. There are many term modules. They are needed to adjust. Oh, okay. This is fin is pulled. Okay, to adjust the timing and direction. Then it is pushed. In this way, the state is changed from 0 to 1. Okay, and finally, the signal goes out from W output. Okay. Anyway, all the 8 cases can be checked by this configuration. Okay. It properly simulates the RM 431. We can finally construct reversible Turing machines in ETPCA 0347. Since we designed a pattern that simulates RM431, therefore, each RM431 is replaced by this pattern, okay, in ETPCA 0347. Therefore, we can finally construct T parity in ETPCA 0347, okay? Here we simulate not T parity, T power. Power of 2 is checking power of 2. This Turing machine checks if the input is of power of 2, okay? On the left side, there is a finite state control. On the right side, tape unit is attached, okay? Tape symbols are stored in this RRAM. This is in state 0. Therefore, tape symbol 0 is stored. Okay. Next, tape square. Also, symbol 0 is stored. 0, 0. In this case, 1. Symbol 1 is stored. 0, 0, 1, 1. This element stores 0. Therefore, anyway, symbol sequence 0, 0, 1, 1, 0 is stored. Okay? Therefore, it should be accepted. By giving a glider signal from begin port, computation will start. Okay, but it takes very much time. How much time? It takes 23 million steps to have an answer. Therefore, we should use hyper-speed mode, high-speed mode. Anyway, by giving a single glider, then computation will begin. Okay. But it takes very much time. Therefore, we use hyper-speed mode. But if we use such mode, glider flies very fast, but therefore we cannot see. Therefore, when it is accepted, then accept bomb will be hit, and an explosion will occur. Okay? By such an explosion, we can see it is accepted or rejected. Okay? Now we use a high-speed mode. It may be very hard to look at the time step, but here is a time. Generation is means the time. Okay. Now 4 million, 5 million, 7, 9, 12, 13, 14, 16, 18, 19, 23 million. Now we slow down. And look at how it will become, okay? Accepted or rejected. Please wait a moment. Flies here, okay? In this way, input 2 is accepted, okay? Now, any Turing machine, reversible Turing machine can be constructed in the cellular space of ETPCA 0347. We saw that any RTM can be simulated even in an extremely simple reversible ETPCA 0347. Construction of RTMs in ETPCA 0347 is greatly simplified by using RLEMs rather than logic gates. This is because there is no need of adjusting arrival timing of 2 or more signals at an RLEM. But it is left for the future study to find other reversible ETPCAs that are Turing universal. Since there are 256 ETPCAs in total. Here are some references. Okay. Thank you for your attention. That's all of my talk.
Thank you so much, sir. It was really enlightening for us. So I am expecting some questions from the audience.
Hello, I have 2 questions.
Yes.
Yes.
Yes. Kenaro?
Hi, dear Kenichi. Nice to see you.
Nice to see you, Kenaro.
Interesting talk. Thank you. I have 2 questions mainly.
Yes.
In this case, for this ETPCA rule 0347, from random initial conditions, this rule is chaotic.
Yes, chaotic. In many cases, it causes an explosion. It becomes chaotic. Yeah.
Okay, okay. So because it is interesting how the class 4 that is related to complex behavior can be not only confined to complex rules or chaotic rules, right?
Yeah.
Okay, thank you. The second question is the universe of reversible Turing machines of the same size of Turing machines?
Pardon? Same size?
Yes, the universe of reversible Turing machines
Yes.
is the same size of Turing machines.
Do you mean how to convert irreversible Turing machines to reversible one? No?
I am thinking more about of enumerate the universe of Turing machines. And if it is in the same size of reversible Turing machines, the universe are the same or one is contained in other?
What do you mean by universe?
Yes, for example, the universe of algorithms can be enumerated, right?
Yeah. Yes.
In this case, the Turing machines is enumerable.
Yes. Of course, both reversible or irreversible Turing machine can be enumerated.
Yes. So
Yeah.
this universe is in the same size.
In some sense, the same size. Yeah. Both are countable, one-to-one correspondence.
Exactly. Okay. Thank you very much, Kenichi.
You're welcome.
Anyone else?
Professor Morita,
Yeah.
I am curious to know how did you find this initial configuration for the computation?
Sorry, I cannot hear well.
Find the configurations as General said that for whether for all random configuration will work. So for the computation, you have shown some initial configuration.
Yeah.
How did you find that?
Yeah. Of course, initial configuration, to find the initial configuration is very difficult, and it should be very carefully designed. Otherwise, an explosion occurs. Yeah. Is it what you asking?
Actually,
I can't hear.
Maybe I can repeat your question.
Sorry.
Maybe I can repeat your question. He is asking whether how you have identified those initial configurations. Those initial configuration looks very much interesting, and it is we can understand that for any arbitrary configuration it might not work, just like you have said. So how we have designed those initial configurations?
Yeah. Of course, resulting configuration is very complex, but they are designed in a modular way. I will show using previous slide. Okay. Yeah, the resulting configuration is very complex, but this is composed of many modules, and the modules are further decomposed of logic element, and logic element is composed of some basic phenomena, and basic phenomena comes from the underlying very simple logical rule, local function. By appropriately find this path is a key point. This is, of course, it was indeed very difficult to find this path. But anyway, I started 3 or 4 years ago. I started from the bottom level, and then find some useful phenomena, collected many useful phenomena, and combining such useful phenomena, I could succeed to realize reversible logic element with memory. And then after that, RLM designing method is used to further constructing complex machines. In such a way, I step by step found a way of designing whole configuration.
Oh, thank you. So difficult task. Okay. Yeah. So I have last question. You are designing the circuits. Okay. My question is
Yeah.
it possible to design general purpose computer using your system? Theoretical is possible, but I'm asking whether it's possible, whether you're thinking about developing general purpose computer architecture using your.
Yes, general purpose. Yes.
Yeah. Are you working on that, or are you thinking of that?
Pardon?
No, are you thinking of that? Designing general purpose computer architecture using your system?
Yes, yes, general purpose computer. Yeah.
You know, are you thinking of the design?
Mm-hmm.
Maybe I should repeat again.
Yeah, yeah.
Sir, sir, he's asking whether your design looks like you can generate a general purpose computer using
Mhm.
your design. So, are you thinking of such a design of general computer architecture using your CA? Just like you were showing to us, a Turing machine can be simulated by your machine. So maybe a computer architecture can be developed by your system. Have you thought of some design? Any general
Yeah,
purpose computer?
yeah. Of course. Up to now, I designed only Turing machines, but rather than Turing machine, more realistic general purpose computer can be in principle possible to implement, but up to now I have not yet tried to do so. Of course, it is a very good problem to be solved.
Very challenging too.
Yeah, yeah.
Okay. So, sir, I have only one query, that is general query to you. Sir, why
Mhm.
you thought of partition CA? What is
Mhm.
the what is the philosophical implication of your partition CA? That is the general query from us.
Uh-huh. Partition CA is mm, came from the idea that reversible, it is a kind of reversible sequential machine by splitting input port and state port. I will show it by wait moment. Sorry. This one. Oh, please wait a moment. This is a scheme of reversible logic element with memory. It has a internal state, and input and output are prepared besides a finite state control, input port and output port. And partitioned cellular automaton in this case, partitioned cellular automaton, these parts are output ports to neighboring cells. And each cell receives a signal from the neighboring cell's output port. Okay, therefore, by distinguishing input and output and central state part, such an idea is the very basis of the partitioned cellular automaton. By distinguish input and output ports and state part. Okay. In the usual cellular automaton, each cell itself works both the state part, central finite control part, and output port part by splitting the state part, internal state part and the output part, we can define its reversibility very easily. That is a key point of partitioned cellular automaton. Is it okay?
Yeah, thank you, sir. Okay, do you have any other questions? If not, then we can thank Professor Morita for joining us and giving it's almost 2 hours of your time we have taken from you. Thank you so much for joining us.
Yeah. Thank you.
Thank you so much for coming here and giving so much excellent talk. Just we are spellbound.
And I want to thank Professor Zenil also. It is like 2 early morning in Mexico and he is joining us. So I want to thank you also for joining us.
You're welcome. I am also happy. I'm very glad to discuss with you. Yeah.
Thank you so much.
Thank you.
Yeah. Thank you.
Okay.
So
Then,
goodbye.
then see you.
See you
Thanks.
See
soon
you.
all. Okay.
Okay. Okay. See you.
Bye, sir.
Bye.